Welcome back to the final video in this series where we're looking at the higher tier only content from the Combined Science magnetism topic at GCSE. We've so far looked at the motor effect, which has told us that if we've got a current flowing through a wire in a magnetic field, that wire will experience a force. We've looked at Fleming's left-hand rule, which allowed us to predict the direction of that force, and we've looked at the equation F equals B times I times L, which has allowed us to predict the size of that force. This final video is going to look at a common application for the motor effect, which is the electric motor. Now, electric motors are used in so many of our everyday devices, and if this had not been invented, our lives would be very different. Think about things from hair dryers and electric drills through to DVD players, and electric cars are becoming more and more popular too. They all use the electric motor, and the principle of the electric motor is simply the motor effect. Now, you can see on the screen at the moment is a diagram of an electric motor, but in order to understand how this works, we're going to look at a slightly simpler case first. What we have on the screen here is a very simple circuit. You can see a cell at the bottom which will pass a current around a coil of wire which is in a magnetic field. Now, when we switch on this circuit, current will flow through the wire and therefore through the coil. And we can see that on each direction and each side, of the coil, the current is flowing in the opposite direction. Now, the field is going from north to south, from left to right. And so by using Fleming's left-hand rule, we can see that the force on each side of the coil will be in the opposite direction. Have a go yourself now at applying Fleming's left-hand rule, but you should be able to see that on the right-hand side of the coil, the force is down, and on the left-hand side of the coil, the force is up. Like we said before, the ends of the coil will experience no force because the wire there is parallel to the field. Now, by having a force downwards on one side and upwards on the other side, that actually produces a turning effect. And so if we look at what happens now, our coil of wire will spin. However, once the coil is upright, it will stop spinning. The reason for this, if this coil continued turning, the force on the right-hand side would be up because the current is now flowing back towards us, and the current on the left-hand side will be down, which will actually just pull the coil back to this position. So although we've managed to get some movement of the coil, what we haven't managed to achieve here is a fully turning electric motor. Because what we would need to happen at this point, if we wanted our motor to carry on spinning, is the forces would have to switch. So the force on this top wire became downwards, and the force on the bottom wire became upwards. And so what we need to do is introduce another part of the electric motor which allows this to happen. I'm just going to run through this animation one more time just to show you those steps again, particularly the movement of the coil, and so hopefully you can see why it comes to rest. Let's now look then at a similar animation, but showing the extra piece of equipment that we put here in order to switch the current. This is a very similar situation. We've still got our power supply, but now here's our coil. Instead of it linking directly to the power supply, we've got this little piece of equipment here, which is called a split ring commutator. Now, the split ring commutator is called this because it's a ring that's got a split down the middle. These grey sections here are what we call brushes. They are just electrical contacts pressing against the metal ring here. Now, what this will mean at the moment, with this in this position, is the current will be flowing in through the orange side of the coil and out through the green side. That will, as before, cause two forces, one on each side of the coil in opposite directions, which will cause it to rotate. However, once it gets to the vertical position, the two parts of the split ring commutator, the two half rings, will be on the opposite side, which means the current will now be going down the green side of the coil and back through the orange. Let me start the animation running and hopefully you'll be able to see what I mean. So what we can see here, let's concentrate first of all on the current. You can see that every half a turn, the current is switching direction round the coil due to the split ring commutator. You can see the grey arrows there changing direction every half a turn. And what that means, I'm just going to get rid of the magnetic field for a minute to make it easier to see. What that means is that the forces on each side of the coil are swapping every half a turn because the current is swapping direction. So what this is meaning is that whichever side of the coil is on the right hand side always has a force downwards, and whichever side of the coil is on the left hand side always has a force upwards. Hence, it causes our coil to spin. Now this version here is very, very much slowed down. A typical motor will be spinning a lot quicker than this. We can speed this one up a little bit, but even this is a slowed down version. Let's just swap back then to the diagram we had at the start, and hopefully you can now start to see some of the key points. We've got the brushes, we've got the split ring commutator, and then up here is the coil of wire where the forces change direction every half a turn in order to keep the coil spinning. And that's the basis of an electric motor. Well, that brings to the end this series of videos on the motor effect. I hope they've been useful to you, and I will see you soon on another set of videos.